Before physics complicates the story, let's begin with the idea almost everyone shares. A vacuum, in everyday language, means nothing. No air, no dust, no sound. If you remove all the air from a room, sound disappears because sound waves need a medium, molecules that can vibrate and pass motion along. No molecules, no sound. Silence. This idea is not wrong, it is just incomplete. For centuries, scientists believed that if you removed all matter from a region of space, you were left with a perfectly empty void, a silent backdrop on which the universe plays out its drama. Isaac Newton imagined space as a kind of rigid stage, unchanging, passive, and empty. Even Einstein at first worked with a similar intuition. And in daily life, this idea works beautifully. Space between planets feels empty. A vacuum chamber removes sound. Outer space is silent to the human ear. So when we say vacuum, we instinctively imagine absolute quiet. But physics is not satisfied with intuition alone. Physics asks a dangerous question. What does nothing actually mean? When scientists tried to answer that question carefully, experimentally and mathematically, the idea of perfect silence began to collapse. Because silence assumes stillness, and nature does not like stillness. Let's stay away from quantum mechanics for a moment. Even classical physics, the physics of everyday objects, already struggles to create perfect quiet. Thermal motion, the unavoidable agitation. Any object with a temperature above absolute zero contains moving particles. Atoms vibrate, molecules rotate, electrons shift. This microscopic motion creates what physicists call thermal noise. Even a solid block of metal that appears motionless is, at the atomic level, alive with motion. Now consider a vacuum chamber. You can remove almost all the air, you can cool the walls, you can isolate vibrations. But as long as the temperature is above absolute zero, 0K, something is still moving. And here's the key point. Absolute zero cannot be reached. This is not a technological limitation, it is a law of nature, formalized in the third law of thermodynamics. No matter how clever your cooling method, you can only approach absolute zero, never arrive. So even before quantum physics enters the story, perfect stillness is already forbidden. But isn't sound gone without air? Yes, but quiet and soundless are not the same thing. Sound is a specific kind of vibration carried by matter. But noise in physics is broader. Noise means fluctuations, random, unpredictable changes in physical quantities. Even in classical electromagnetism, empty space can host electromagnetic waves, radiation passing through, energy fields. The vacuum is already less empty than intuition suggests. But the real shock comes when we push deeper, because classical physics, for all its success, still assumes that zero is possible. Quantum physics disagrees. Quantum mechanics begins with an unsettling claim. You cannot make everything exactly zero at the same time. This is not philosophy, it is mathematics, the uncertainty principle. Werner Heisenberg showed that certain pairs of physical quantities cannot be simultaneously known or fixed with perfect precision. The most famous version relates energy and time. Delta E times delta T greater than or equal to h bar over 2. This inequality has a startling implication. If you try to define a system with exactly zero energy for any duration of time, you violate the uncertainty principle. In other words, a perfectly quiet vacuum would require perfect zero energy. Quantum mechanics forbids this. Zero-point energy. Every quantum system has a ground state, its lowest possible energy, but that lowest energy is not zero. Even when a system is as calm as it can possibly be, it still fluctuates. This residual energy is called zero-point energy. It doesn't come from heat, it doesn't come from particles, it doesn't disappear. It is built into the structure of reality. Vacuum fluctuations. In quantum field theory, empty space is not empty at all. Every point in space is filled with fields, electron fields, photon fields, quark fields. These fields cannot sit still, they fluctuate. Particles briefly appear and vanish. Energy rises and falls. The vacuum seethes with activity. This is not metaphorical noise. So far, we've spoken theoretically, but how do we know that the vacuum is alive, noisy, and restless? Enter the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. What it is: place two extremely thin, uncharged metal plates very close together, on the scale of nanometers, in a vacuum. Classical physics predicts no force. There should be nothing to push or pull the plates. Quantum physics, however, predicts a measurable attraction. Why? Because the vacuum is not empty. The zero-point fluctuations of electromagnetic fields outside the plates are slightly different than inside. Fewer fluctuations exist between the plates, creating a tiny pressure that pushes them together. This is direct evidence that empty space is not silent, still, or nothing. It has energy, it moves, it acts on matter. Real-world implications. The Casimir effect is not just a curiosity, it has implications in nanotechnology. Moving parts in microchips and MES devices experience Casimir forces. Fundamental physics helps confirm predictions of quantum electrodynamics, QED. Cosmology contributes to understanding vacuum energy and dark energy. To go even deeper, we need to abandon the picture of the vacuum as empty space. Quantum field theory redefines it. Every type of particle is an excitation of a corresponding quantum field. Even in the lowest energy state, these fields never rest. Virtual particles continuously pop in and out of existence. This means that empty space is a boiling, restless sea. The vacuum is never still, never silent, and never truly empty. Spontaneous particle creation. Virtual particles contribute to phenomena like Hawking radiation near black holes. Vacuum energy may explain the observed acceleration of the universe, dark energy. Casimir and Lamb shifts, small measurable energy differences caused by vacuum fluctuations. Reference Peskin and Schroeder, 1995, An Introduction to Quantum Field Theory, Addison Wesley. Vacuum fluctuations are not an abstract mathematical detail. They leave fingerprints across the observable universe. During cosmic inflation, space-time expanded at an extraordinary rate. Quantum fluctuations that normally exist only at microscopic scales were stretched to astronomical sizes. These tiny variations in vacuum energy became the seeds of structure. Every galaxy, every cluster, every large-scale filament traces its origin back to quantum noise in an early vacuum state. This is not speculation. It is encoded in the cosmic microwave background, the faint afterglow of the early universe. Satellites like COBE, WMAP, and Planck measured minute temperature variations, exactly matching predictions derived from vacuum fluctuations. In this sense, the universe is not merely influenced by the vacuum, it is written by it. Classical intuition treats the vacuum as a passive backdrop. Modern physics rejects this view. In quantum field theory, the vacuum behaves more like a material with properties. It has energy density, it can exert pressure, it can polarize, it can respond to boundaries and fields. This is why light bends near massive objects. Vacuum structure couples to space-time curvature. Virtual particles affect the motion of real particles. Forces emerge even when no classical source is present. The vacuum is not a stage, it is an actor. One of the clearest demonstrations that the vacuum is active comes from vacuum polarization. Place an electric charge in empty space. Classical physics says the electric field simply spreads outward. Quantum physics predicts something subtler. The vacuum rearranges itself. Virtual particle-antiparticle pairs briefly appear, partially screening the charge. As a result, the measured electric charge depends on distance. At short distances, the charge appears stronger. At larger distances, weaker. This is not an experimental artifact. It has been measured precisely in high-energy particle experiments. The implication is profound. Fundamental constants are shaped by the vacuum itself. What we call charge is not an intrinsic number alone, it is a vacuum-modified quantity. In 1947, physicists observed something impossible according to classical theory. Two energy levels in hydrogen, predicted to be identical, were slightly different. This discrepancy became known as the Lamb shift. The cause was not experimental error, it was the vacuum. Vacuum fluctuations slightly alter the electromagnetic field around the electron, shifting its energy levels. The effect is small, but measurable. This was one of the earliest and most convincing confirmations that empty space affects atomic structure and vacuum fluctuations have observable consequences. Without vacuum noise, atoms would not behave the way they do. Near a black hole, the vacuum behaves in extreme ways. Strong space-time curvature distorts quantum fields. Vacuum fluctuations near the event horizon can separate, with one part escaping as Hawking radiation while the other falls inward. This process does not require particles falling in. It requires only a horizon, a vacuum, and quantum mechanics. Black holes slowly lose mass because the vacuum is unstable in curved spacetime. This reveals a critical insight. The vacuum depends on geometry. Change spacetime and the vacuum changes with it. Not all vacuum states are equal. Quantum field theory allows multiple vacuum configurations. Some are stable, others are metastable, known as false vacua. Our universe may exist in such a state. If a lower energy vacuum exists, a quantum transition could occur, forming a bubble that expands at near light speed, rewriting physical laws within it. This is not science fiction. It follows directly from known field equations. No alarm is warranted, the timescales are vast, but the implication is staggering. The laws of physics may be contingent on the vacuum we occupy. At this depth, the idea of silence dissolves. Soundlessness refers to pressure waves in matter. Quietness suggests stillness. But the vacuum has neither condition. It has fluctuations without particles, energy without motion, and structure without substance. Asking whether the vacuum is quiet is like asking if zero is heavy. The question itself assumes classical intuition that no longer applies. Despite everything we know, the vacuum remains one of the least understood entities in physics. Open questions include why vacuum energy is so small compared to naive quantum field predictions, how vacuum structure emerges from quantum gravity, whether spacetime itself is a vacuum state of a deeper theory. Each of these problems forces physics beyond established frameworks. Quantum field theory predicts an enormous vacuum energy density. If this energy gravitated normally, the universe would curl into itself instantly. Instead, observations show that vacuum energy, associated with dark energy, is extremely small but non-zero. The mismatch between theory and observation exceeds 120 orders of magnitude. This is not a rounding error. It is the worst prediction failure in the history of physics. No known symmetry, renormalization scheme, or cutoff resolves it cleanly. Any explanation must fundamentally revise our understanding of energy, gravity, or the meaning of vacuum itself. Quantum fields naturally generate infinities. Rather than discard the theory, physicists developed renormalization, a systematic way to absorb infinities into measurable quantities. Renormalization reveals a critical fact. Physical laws depend on scale. The vacuum at one energy scale is not the vacuum at another. This scale dependence explains why forces change strength with energy, why constants are not truly constant, and why the vacuum must be described relationally, not absolutely. The vacuum is not a single object. It is a hierarchy of behaviors across scales. In modern physics, the vacuum is often treated as effective, not fundamental. An effective vacuum is the lowest energy state relative to a given description. Examples: the vacuum inside a superconductor differs from free space. The vacuum near a horizon differs from flat spacetime. The early universe vacuum differs from today's vacuum. This implies that reality itself is layered. What appears fundamental at one scale dissolves into collective behavior at another. Several modern theories suggest spacetime is not fundamental. Instead, it may emerge from quantum entanglement, information networks, or collective vacuum degrees of freedom. In these models, geometry is secondary, distance is derived, locality is approximate. The vacuum is no longer inside spacetime. Spacetime is inside the vacuum. Even in its lowest energy state, the vacuum is highly entangled. Regions of empty space are quantum correlated regardless of distance. This entanglement stabilizes spacetime, governs horizon thermodynamics, and links gravity to information theory. Removing entanglement would not quiet the vacuum. It would dismantle spacetime itself. Different observers disagree on what counts as vacuum. An accelerating observer detects radiation in empty space, known as the Unruh effect. To an inertial observer, nothing is there. This means the vacuum is observer-dependent. Quietness is not absolute. It depends on motion, frame, and horizon structure. Vacua obey thermodynamic laws. They possess temperature, in horizon contexts, entropy, proportional to area, and equations of state. Black hole entropy and de Sitter temperature arise directly from vacuum structure. Thermodynamics is not imposed on spacetime. It emerges from the vacuum. Every attempt to quantize gravity confronts the vacuum. Loop quantum gravity, string theory, and holographic models all predict discrete vacuum microstructure, modified spacetime fluctuations, and departures from smooth geometry at Planck scales. No theory is complete, but all agree on one point: the vacuum is not optional. It is the primary arena where future physics must operate. At extremely high energies, empty space stops behaving like emptiness. Virtual particle-antiparticle pairs momentarily appear and distort electric and magnetic fields. This effect is called vacuum polarization. As a result, charges are partially screened by the vacuum itself. This means the strength of a charge depends on distance. The vacuum modifies forces actively. Empty space behaves like a responsive material. In strong fields, near heavy nuclei or neutron stars, this effect becomes measurable. The vacuum bends interactions before matter ever enters the picture. Because the vacuum reacts differently at different energy scales, fundamental constants are not fixed numbers. The fine structure constant changes with energy. Coupling strengths drift as interactions probe smaller distances. This implies constants emerge from vacuum structure. Laws of physics are scale-dependent. Fundamental may mean effective. The vacuum is not a background. It participates in defining the laws themselves. Our universe may not occupy the lowest possible vacuum state. Particle physics suggests the current vacuum could be metastable, stable for now, but not forever. A lower energy vacuum could exist, separated by an energy barrier. If a transition occurred, physical constants would change instantly. Atoms would no longer exist. Space-time itself would reconfigure. No warning, no sound, just a shift in what reality allows. The vacuum is quiet, but it may not be permanent. During cosmic inflation, microscopic vacuum fluctuations were stretched to astronomical scales. These fluctuations became density variations, formed galaxies and clusters, imprinted patterns in the cosmic microwave background. Structure did not arise from matter. It arose from vacuum noise amplified by expansion. Every galaxy traces back to a moment when nothing briefly failed to stay uniform. Quantum theory allows regions of negative energy density as long as they are temporary and compensated elsewhere. This is not science fiction. It is required for Hawking radiation, Casimir forces, certain space-time geometries. Negative energy shows the vacuum can violate classical intuition without breaking physical law. The vacuum is constrained, but not classical. We never observe the vacuum directly. We infer it through force shifts, spectral changes, noise correlations, missing energy. Every vacuum measurement is indirect. This raises a deep issue. Are we studying the vacuum itself, or only how matter fails to ignore it? Physics may be probing the shadow of something deeper. At quantum scales, silence loses meaning. Noise is unavoidable. Fluctuation is mandatory. Stillness violates uncertainty. A perfectly quiet vacuum would contradict the mathematics that allows existence at all. Silence is not the natural state. Activity is. Quantum field theory predicts that vacuum fluctuations are correlated even between regions that cannot exchange signals. These correlations do not transmit information, do not violate causality, but do encode structure beyond space-time separation. They arise because the vacuum is a global quantum state, not a collection of local ones. Local measurements sample a much larger, inseparable whole. The vacuum is not stitched together point by point, it exists all at once. Vacuum fluctuations are not uniform across frequencies. Each quantum field contributes a characteristic noise spectrum. Low-frequency modes dominate large-scale structure, high-frequency modes dominate local interactions. Cutoffs are required, not because physics fails, but because measurement does. Every detector defines the vacuum it observes. Noise is not a flaw, it is the observable imprint of quantum fields. Fluctuations do not merely exist in spacetime, they act on spacetime. Vacuum stress energy contributes to curvature through Einstein's equations. This back reaction limits spacetime smoothness, induces metric fluctuations, constrains semi-classical gravity. At sufficiently small scales, geometry itself becomes noisy. Spacetime is not a stage, it responds. To model vacuum back reaction, physicists use stochastic gravity. Instead of a smooth metric, spacetime is treated as a fluctuating entity driven by vacuum stress correlations. Predictions include horizon jitter, light cone blurring, fluctuations in causal structure. Classical geometry emerges only after averaging over vacuum noise. Smoothness is an approximation. Time asymmetry may arise from vacuum structure. While microscopic laws are time-symmetric, vacuum states encode boundary conditions, define ground state stability, constrain entropy flow. The direction of time may reflect how the vacuum organizes fluctuations, not how particles move. Time may not flow, it may relax. Zero-point energy cannot be extracted to do work. This is not a technical limitation, it is a fundamental one. The vacuum enforces passivity, stability, and energetic consistency. Attempts to exploit vacuum energy fail because the vacuum defines the baseline itself. It is not empty fuel, it is the reference. Negative energy is allowed, but tightly regulated. Quantum inequalities restrict magnitude, duration, and spatial extent. These constraints prevent macroscopic causality violations, space-time instabilities, exotic engineering loopholes. The vacuum permits strangeness, but only briefly and locally. Freedom with rules. In curved space-time, the concept of vacuum fragments. There is no unique ground state, no universal particle definition, no observer-independent quietness. Each geometry defines its own notion of emptiness. The vacuum is contextual. Vacuum regions can possess entropy even when no particles are present. This entropy scales with boundary area, arises from entanglement, dominates horizon physics. The vacuum stores information without storing matter. Nothingness remembers. At Planck scales, quantum field theory ceases to apply. Predictions become regulator-dependent, non-local, and background-sensitive. At the deepest level, the vacuum may not be a thing at all. Modern physics increasingly treats it as a boundary condition, a rule that constrains what can exist, not a material that exists itself. Fields, particles, and space-time do not sit inside the vacuum. They are permitted by it. The vacuum defines the limits of possibility rather than filling space with content. A universe with true nothingness would have no structure to define laws, measurements, or even absence. Without a vacuum state, energy cannot be defined. Stability has no meaning. Fluctuations have no baseline. Absolute nothingness is not silent. It is mathematically incoherent. The vacuum exists because physics requires a reference, not because something must fill space. Why do physical laws have their specific form? One possibility, the vacuum selects them. Different vacuum configurations allow different particle spectra, constants, and symmetries. Only some configurations permit long-lived structure. In this view, laws are not imposed, they are realized. They survive because the vacuum allows them to. Physics becomes environmental rather than absolute. This does not require philosophy or speculation. If many vacuum states are possible, then most are hostile to complexity. A few allow chemistry, stars, observers. We observe this vacuum not because it is special in principle, but because it is stable enough to be observed at all. The vacuum does not favor life. Life favors survivable vacua. As experiments push deeper, they increasingly report null results. No breakdown of relativity, no detectable space-time discreteness, no observed vacuum decay. This silence is not failure. It suggests that the vacuum is extremely stable, highly constrained, resistant to disturbance. The deeper we probe, the more rigid the foundations appear. Some questions may never be answered within physics. Why this vacuum? Why these constraints? Why existence rather than inconsistency? At a certain depth, explanations stop reducing and start terminating, not because we refuse to ask, but because there is nothing simpler beneath. Early physics explained how things move. Later physics explained why they move that way. Vacuum physics increasingly explains what must be true for anything to exist at all. Mechanisms give way to constraints. Processes give way to consistency. The vacuum is not dynamic in the usual sense. It is structural. The vacuum is never quiet, not because it is noisy, but because quietness requires absolute rest. Absolute rest requires absolute definition. The vacuum refuses absolutes. Fluctuation is not activity. It is the price of definability. Physics approaches the vacuum the way mathematics approaches infinity, closer with every step, never arriving. Each theory refines the boundary, none dissolve it. Understanding increases, finality does not. The vacuum is not emptiness, not energy, not noise, not mystery for its own sake. It is the minimum structure reality requires to exist without contradiction. Nothing quieter is allowed. Nothing simpler is stable. And that is where physics, for now, must rest.